screen?
Yes, thanks.
There you go.
Thank you, Jason. We are missing many people, I feel.
Yeah, that's nice.
It looks a bit empty.
It looked quite empty. When the students busy with exams. So.
Yeah, something maybe. Anyway,
Is this okay, or you want all the lights?
all the lights off.
All the lights, okay.
Actually, it might help if you lower that. That's probably messing up. Yeah, the angle is some off. Go to the left. Yeah.
Yeah, so remote people, can you see and hear? I mean, can you hear and see and hear my presentation?
Ping is on one.
Ping?
Yes, I can see it.
Okay.
Okay.
You go.
And Chris?
She may
Chris is not in here. Chris is on vacation.
Okay. And who came, right?
Yeah.
There's time there, so don't worry. Ping
Okay.
everybody from here.
Okay.
One person can do it. I think
Yeah.
it's fine. It's
It's fine.
Yeah, okay. Okay, so the title is Ensemble-Based Sensitivity Estimates of Oil Transport to Initial Condition and Forcing During the Deepwater Horizon Oil Spill. I've been talking about this for a while now. So the main objective of this work is to quantify the pathways of transport of oil and its uncertainty during the BP oil spill in the Gulf of Mexico using an ensemble-based approach. But broadly speaking, we want to design a probabilistic forecasting system for the Gulf of Mexico, particularly investigate the effect of accounting for uncertainty in initial conditions and atmospheric forcing. Here is the domain used in this work. So as you know, this is the Gulf of Mexico domain. The magenta diamond over here shows the site of the oil spill. This occurred in 2010 April, and the oil spill started on 20th of April, and it was sealed about 3 months later. The color shows you the bathymetry. So at deepest point, it is about 4,500 meters depth. But as you can see, very close to the coastal areas, or not very close, but in the coastal areas, the depth could be less than 1,000 meters and even sometimes 500 meters, at some locations 500 meters. So here are the details of the model. So number of levels in the model is 50. The model uses ROMS. The resolution is 9 kilometers, which makes the grid about 250 by 200 points. The initial and lateral boundary conditions are obtained from HICOM. This is the global product of HICOM, 0.08 degrees resolution, which is about 9 kilometers. So this global product is available only once a day, at 00Z. So I use this to generate, to do the get the initial conditions and the LBCs. The surface forcing is from ECMWF, and the ensemble size throughout this work used is 20. So whenever I mention ensemble, the size used is 20. This has not changed throughout the work. So something about probabilistic forecasting. So let's say you have access to a global analysis. These can be used to launch a deterministic, which is also called a control forecast. So throughout, now I'll say control forecast rather than deterministic forecast. So it simply means launching a single forecast from an initial condition. Now let's say you want to launch a probabilistic forecast, then you need perturbed initial conditions. So actually you need a PDF, and you want to integrate the PDF forward in time. But integrating this PDF is extremely computationally costly, because this PDF would be million dimension, the same dimension as the model. So a cheaper way to do is using using Monte Carlo samples, or as it is called in atmospheric and ocean studies, ensemble methods. So you need a PDF, and from that you draw a small size of ensemble samples, and you integrate those in time, and then at any given time the PDF defined by that sample is your forecast PDF. It has mean, standard deviation, and other moments. So higher the number of ensemble members, the better, but there are severe restrictions on how big that size can be because of limited computational resources. So in this work, the size is 20. Now, you simply cannot draw this perturbation from any PDF. These perturbations should be consistent with the dynamical structure of at that particular state. And the state changes in theory with time. So in theory, it changes two different minutes, 2 different hours is going to have 2 different dynamical structure, but it could be kind of similar for one season. But it all depends upon location and time and so on. So in general, the state of the atmosphere and ocean changes, and the structure of uncertainty defined by the dynamical structure of the underlying attractor is going to be different at different times. So ideally, you want to sample from the structure that is valid for that particular initial condition or that particular initial time from which you are launching the forecast. So the breadth vector technique produces such perturbations given global analysis. So I would like to point out that probabilistic forecasting, what I just talked about, gives the impression that only the perturbation should be in the ICs, initial condition, but this is not true. We have to account ideally for all the sources of uncertainty. So ICs is just one source of uncertainty. There can be, there is always some errors in the boundary conditions, and then there is error in the model. So all these sources should be ideally accounted for. And accounting for the initial condition uncertainty is just a part of this game. Again, ICs is also important, and in general, there is no answer to which one is more important. It depends upon the model and domain and so on and so forth. There are some studies that compare which uncertainty is more important, but usually all play a role at different time scales. So the breadth vector method addresses the initial condition uncertainty part. It produces a perturbation that are consistent with the uncertainty structure at that particular point of time. So here is an example of an ensemble forecast. So the y-axis shows some variable, and the x-axis is forecast time. So the cyan, the light blue are the ensemble members, and they are sampled from some PDF valid at time t equal to 0, and they are integrated in time using the model. The blue solid line shows the ensemble mean, and the yellow line shows you the observations. Okay. I have not showed here the control forecast, which would be another curve, a single curve on this graph. So ideally, what should happen is, if you're sampled correctly from the initial distribution, then the ensemble mean should have a lesser RMSC than the control. So RMSC here is basically the difference between the yellow line and the blue line. Okay. At every point, you got some RMSC, and you can use a suitable metric for calculating the RMSC. I mean, RMSC itself is well defined, but what exactly you want to compare, like 800 meter MV height or temperature, whatever, you can make a choice. So RMSC is basically quantifying how much of error is there in the ensemble mean. But the ensemble provides you with much more information than a control forecast, and that's why ensembles are very important. So what more information it produces, it gives you the expected error. So expected error is given by the spread of the ensemble, and one way to quantify the spread of ensemble is standard deviation. You can think of just taking the difference between the two extreme ensemble members. That could also quantify the spread. But the point is that it is called expected error because at time t equal to 0, when you launch the forecast, this yellow line has not happened yet. So at any given lead time, it gives you the best the most likely forecast, the most likely which is given by the mean, but also gives you an error in that mean. So rather than saying the temperature tomorrow is going to be 35 degrees Celsius, it says 35 degrees Celsius plus minus 5 degrees. So you get more value or more information out of the ensemble. That's why ensemble is very important. So this spread is called the expected error, and it usually grows with time. Now, apart from getting the RMSE low, one more thing that should happen if your probabilistic system is good enough is that this expected error should be equal to the true error, which is RMSE. So true error you will come to know only after the observation happened. At that point, you can check whether your expected error was equal to or more or less equal to the RMSE. Because what that would tell you is that whatever error your probabilistic system said that would occur actually occurs. Okay, so if I'm saying it's going to be plus or minus 5 degrees Celsius, but actually the error is more than 5, then my system has underestimated the error. Okay, so these are the two characteristics of a good probabilistic system. One is the mean should be better than the control forecast, and the expected error should be comparable in magnitude to the RMSE. Now, to get this good characteristic of a forecasting system, probabilistic forecasting system, it is important to construct the ensemble correctly. So what does correctly mean? Correctly means once, as I told you, getting the correct structure of the initial condition uncertainty, sampling from it correctly, having as many ensemble members large as possible, and also if you have got errors in boundary conditions and model error, that also should be sampled correctly. So the boundary conditions also have a structure, the model error might also have a structure, and we are not talking about that. I'm not going to talk about that. So to get this initial condition structure correct, we are going to use something called the breadth vector method, BEM. So this is a very general technique that can be used with any model. So let me give a general description rather than going into the ROMs. So what you basically do is you perturb your, suppose you have access to this global analysis given by these red diamonds, okay, at every time interval of delta t, where delta t is t2 minus t1 and t3 minus t2 and so on. So this t1 minus t2 is called the length of the breadth cycle. Then you have your control. So you basically integrate your control forward in time up to time t2, okay? And at time t1, you perturb your variables, one variable or several of them, randomly. And then you integrate so that you have a sample of say 5 or 6 or n, which is the ensemble size, and you integrate those that ensemble forward in time. At time t2, find out the mean of the ensemble. Okay, find out the perturbations with respect to the ensemble, with respect to the mean, and add those perturbations to the analysis that is valid at time t2. And then again integrate up to time t3, find out the mean, find out the perturbations, and add those perturbations to the analysis at time t3. So this adding to the analysis makes sure that your ensemble remains close to the observations, because analysis is kind of observations. And then this perturbation will start generating a structure, okay, which is called the growing mode of the system. And after doing for many cycles, the perturbation will grow very, very large. So you rescale to a particular magnitude, and you continue that process. So when you repeat this process many times, your leading mode, the ensemble perturbations will capture the leading mode of the system, the growing mode of the model or system. So the perturbation tend to project on the growing modes, thereby leading to amplification in perturbation magnitude. The breadth vectors are periodically rescaled to keep the magnitude small. The leading breadth vector picks up the dominant mode corresponding to the time scale of the breeding cycle. In this work, the length of breeding cycle is 1 week. So here is the breadth vector method in the ROMS model that I have implemented. So the experiment starts on 26th of Jan 2010. So at 26th on Jan 2010, I have perturbed the temperature randomly by 5% everywhere in the domain. So each of these magenta curves is showing you the absolute value of one perturbation, of one ensemble member. So there are 20 of these lines. Okay, and you don't see negative values because I've taken the absolute value and have averaged over the whole domain. Okay, so at time t equal to 0, of course, the perturbation is 0 in, I'm showing you these perturbations in UV field, okay, and I perturbed the temperature field so that in the UV field there is 0 perturbation at time 0. And then because of the perturbation in temperature, the perturbations are induced in the U and V field, and the perturbations start growing. And as you can see, after every week, I'm adding these perturbations to the analysis, HICOM analysis at that particular week. Okay, so on 23rd, I start the rescaling. So this is 23rd of March. So after 23rd of March, I integrate and rescale to a particular value of 0.05 meters per second, and I keep rescaling so that the magnitude does not grow in a unbounded way. So 20th April is the time of the spill. So yeah, I've got total 23 weeks, and neglecting the rescale, the spin up time, if you want to call it, I got about 15. So the aim here is to see how the ensemble performs in forecasting the Gulf of Mexico Ocean. Okay, so for this I have done 4 different experiments. So all the forecasts are 15 days, and they're launched from each of the date time groups. Okay, shown here on the x-axis. Okay, I have got these perturbations on each of the week, and I'm launching forecasts from them. So there are 4 different experiments. So the ECMWF forecast control and ensemble for the surface for 15 days are downloaded. So for this particular year, there's a website, there's an experiment called TIGGAE. So what TIGGAE is different operational centers in the world have agreed on a common platform, and they upload their ensemble members to that website. So you can get ECMWF, NCEP, so on and so forth, whatever fields you want. So I downloaded their control and ensemble for the surface for 15 days. From each date time group, I have 15 days forecast, atmospheric forecast at the surface. So there are these 4 forecast experiment. There's a control forecast. Okay, so what does the control forecast use? It uses the HICOM global analysis as the initial condition at each date time group, and it uses the ECMWF control of the atmosphere as the forcing. So there is no ensemble members involved in the control forecast. It's just a single forecast starting from a HICOM initial condition given by the global analysis, and there is a deterministic control, deterministic forcing from ECMWF. The rest of these 3, green, blue, and red, are ensemble forecast. So the second one, the green, what it does is it uses the HICOM initial condition. So there is no ensemble in the initial condition, but it uses the ECMWF ensemble forcing, which I'm calling perturbed forcing. Okay, so 1 to 20 members, each one has the same initial condition, but each one is forced by a unique ensemble member from ECMWF.
What about the atmospheric initial condition?
Well, that is because this is a uncoupled run. This is ocean only. You understand?
Ocean only, okay.
Yeah. So this ECMWF thing has been downloaded.
Okay.
It's ocean only. Then the blue one. So in this green experiment, though the initial condition is the same for all the 20 ensemble members, because the forcing is different, it will each of the ensemble members will eventually diverge from each other. In the third experiment, the ensemble forecast, it is just the opposite of the green one. So I'm using the perturbed initial condition, but the control forcing. So each of the ensemble members 1 to 20 has a different initial condition, but the same forcing. So the different initial conditions come from the red vector that I just showed. So at the beginning of each week, I've got access to 20 perturbations. So I add those perturbations to the HICOM analysis, and we have 20 ICs at every grid point for every variable. And the red, the fourth experiment, has an perturbed initial condition and perturbed forcing. Okay, so in each of these experiments there is something different. So we come to know exactly the effect of including the perturbation from initial conditions and forcing, and lastly when we include both, this uncertainties.
So for the last one, you just make a random perturbation and random initial condition. You just associate them randomly. Right.
The generation you understand is from this, right?
Right.
The generation. Yeah. So the first and first, like that, you mean? Yeah, that is just whatever it is.
It's arbitrary.
It's arbitrary, whatever it is. The first of ECMWF goes with the first red vector of this. So the RMSE for ensemble forecast calculated from the mean. The HiCom analysis is used for verification, and we'll talk mostly, almost exclusively about the surface velocity field. Okay, so RMSE for control is clear. You just take the HiCom as observation and subtract from the control run. But for the ensemble, first you find out the mean, and the RMSE is with respect to the mean. And HiCom analysis is used for verification. So whatever product I used to generate ICs and lateral boundary condition, the same product is used for verification, and we'll talk mostly about surface velocity field. So RMSE statistics are calculated over different boxes and averaged over all date time groups. The biggest box that you see over here, the black one, I'm just calling it big box, and the green boxes are the coastal areas. So I have got the South US coast, which includes the site of the spill. Then I've got Florida. Then this green box down I'm calling the Max coast, the Mexican coast. This I'm calling the central coast. And then there are two areas that are inside the ocean, that is the loop current area, and I'm calling this region the far field. I mean, the names don't mean much, but just a convenient. So when I say big boss, it includes this. I just wanted to stay away from the boundaries a bit, and anyway, this is the core area of interest. So I'll show you the RMSE error statistic calculated over different boxes, and these are all averaged over all the date time groups. So in this slide you see on the y-axis the RMSE in meters per second, and it is averaged over the big box over the all the date time groups, of course. And this is the error for the control forecast. Okay.
So for the RMS error, you do that difference at each grid point and average over the box, right?
That's correct.
It's average RMS error.
So first, for a given date time group, RMS is calculated. That is straightforward. For a given date time group for a given time, that is straightforward. Yeah, I know what I was skipping. So I do it separately for each date time group and then average it. So you're saying that
Spatial. So you find the RMS error at each point and average over the box, or this RMS error with the average velocity.
Oh, at each grid point average.
You compute the RMS error first at each grid point, and then you average over the box.
Yeah.
Okay.
What is it? So summation of xi minus yi, where I is the grid point.
So he's basically asking about the step 1, step 2. Step 1 is calculating RMSE at each grid point.
Yeah, and then I will
Step 2 is
go to
averaging it over the big box.
Yes.
You can do the other way around.
Because the way you've written it could be either one.
No, at each grid point first, and then average over the domain.
Yeah.
Because the way you said velocity averaged over big box, which is
I think first averaging observation separately and control separately, and then taking the difference.
no. I'm just saying how you did it.
Yeah, but that I think nobody does, right?
Okay, that's fine. The way you wrote it there, it's
Yeah.
confusing.
At grid point, doing grid point first is the correct way, I think. I thought you were asking over like this. After doing for each date time group, we can average date time group. That's one possibility. Other
I think
possibility is concatenate all the date time, which I did not do.
What you're doing is right. I just wanted to confirm.
Right. But I mean, the other possibility which I did not do, I don't know what the correct thing is to. I did date time group separately and then average. You could concatenate all the grid points in date time group.
Yeah, that may change slightly.
That may change, I think, but I don't know. But that's this is more convenient, like in terms of writing a program.
It probably won't change much. It's a question of whether you average the square root of the square. So it's
Right. So
slightly different.
Right. So the point here is that the error in control forecast at any time is due to these four things. Three things: error in the initial condition ICs, error in the boundary conditions, and error in the model. This is a very general statement I'm making. This applies to any atmospheric ocean forecast.
So in this case, it's not error in the model. It's a difference between your model and HiCom. They're both models.
Yeah, I mean, one has to treat something as truth.
Ideal sense.
That's it. If you truth, I mean, at the end of the year, for this study, HiCom is the truth.
Because you guys know HiCom itself has errors.
Yeah, obviously, obviously. But you define. But this is a common problem in our field, right? You define something as truth.
No, but you can't expect your model to reproduce HiCom model's error.
No, but
its own error.
No, but the point is that ROMS is not matching HiCom because there is something difference in the two models, right? You agree with that?
Right.
Yeah. So that's what I mean.
It's more like difference between models.
Different between models. So this error in model is that there's a difference between the two models. That's why.
If it was true observation, then you could say.
Error.
Yeah, but we never have. We went through observations have errors. So.
Terminology difference, I guess.
But in the atmosphere, the reanalysis mostly agree.
No, but reanalysis is a very good analysis because it uses a lot of data.
No, the atmosphere, NCEP and ECMWF, they pretty much agree on most things.
No, but the same observations are going.
They don't agree. HiCom and other reanalysis, they all agree.
No, but that's because atmosphere is a lot of observation and the same observation go into both the things. So
that's
the probability of matching is far more.
Yeah.
So this is a very general statement. And in the context of ocean, the boundary conditions themselves are grouped into two. There's the lateral boundary conditions and there is the forcing. So in this work, I've just investigated the ICs and the forcing. Okay. So this is what the blue line shows you, the mean of the RMSE in the mean of the ensemble that uses the perturbations in initial conditions only. So, and this is only at the surface, average over for the surface case. So you see that the difference is not, it improves, which is consistent in time, but the difference is not very big. Now the green one shows you the mean RMSE in the mean of the ensemble that uses perturbations in the forcing only. So if you had to make, according to this graph, you had to make a choice in perturbing either the ICs or the FCs, you would say let me perturb FCs because that's giving you a better advantage, more advantage.
What is FC?
FC is the perturbed forcing. So
it's basically lateral boundary condition or
no, perturbed surface forcing. So
meaning SST.
Yeah. So this is the second. The green experiment uses the same initial condition for all the ensemble members, but each ensemble member has a different member of the forcing from ECMWF. And this blue one has different ICs but same forcing, and the red one is the most general. So as I pointed out over here, in this work we are talking only about perturbed ICs and perturbed forcing. And then if you combine both the perturbations, you get the red curve, which is kind of addition of the green and the blue. So again, it's not a huge one, but average over the big box, you do get some advantage, consistent advantage in perturbing both the ICs and the FCs.
So, but
yeah,
suppose your IC spread depends on how efficient your breeding vectors are in producing the perturbations.
That's right.
So if you took your perturbations, multiplied them by.
I did that.
You did that.
I did
okay.
that. So I found that I multiplied up to a factor of 1.5. I did 1.1 and 1.2, 1.5. Above that, even with 1.5 factor, a lot of ensembles members start blowing up.
Okay.
That's
so it can't just blow up the initial.
It's not arbitrary because there's a limit because you end up throwing things out of balance.
Because it's somewhat arbitrary a normalization, right? You can tweak that.
Yeah, and because at some magnitude it starts blowing up, there's a natural limit in some sense. I mean, a practical thing.
It blows up in the breeding vector process.
No. The breeding vectors are stored.
Okay.
And then you can rescale them, right?
Okay.
So I did experiment 1.1, 1.2, 1.5. After 1.5, a lot of them start. We can also rescale the forcing perturbations actually.
But what if you recomputed the breeding vectors with higher, allowing them to be bigger? Yes, so that's slightly different.
Yes, that's slightly different. But
I think you did that before, trying to make
the bigger. But I did not do by rescaling. The starting of magnitude, that I raised, so that at any given point of time, the magnitude is higher. I did rescaling both in ICs and FCs, and after some, and multiplying by factor of 1.5 is not getting the blue curve very, very down. So I just gave up, and that's why I'm not using any rescaling of magnitude in this work. It is whatever the ECMWF has given me and whatever the ICs breeding vector is. Yeah.
Just a basic. So what does the BVM doing here? How does it help?
Right. The other thing is that if there is some instability in the system, usually there is in the model, in the domain that you're talking about. Okay, so you can imagine this structure as an ellipse in 2 dimension or as an ellipsoid in n dimensions. So in this model, it will be a million-dimensional ellipsoid, and it will have a principal axis. Okay, and this ellipsoid will keep changing in time. That's what I mean by the dynamical structure of uncertainty keep changing in time. And you want to get that ellipsoid at that particular time. And usually with 20 ensembles, you don't get it. You want to get the principal axis, which is the growing one. So what happens is eventually, even if your initial perturbations at time table 0 are random, they eventually start projecting on the growing mode.
Okay, so essentially what it helps you to keep it on a growing mode, and so in the end you get errors in the growing mode because of the growing mode.
Error aligned along the growing mode.
Okay.
Because you want to, given a choice of capturing three dimension out of million, you would like to capture the 3 most growing ones to account for the most amount of uncertainty. So this spread that I talked about, which should be comparable to the RMSC, that will be good enough, good in the sense high enough, only if you have captured the growing mode.
Great.
And that's the reason why otherwise one could have actually, I have not done this experiment, just perturb randomly and compare it with this guy. I think
if you could do infinite ensemble, you could just perturb randomly. But if you want to do a very small number, then you have to pick the perturbation that give you the most spread, because those are the ones that are going to control the algorithm.
It's kind of an analog, like how we look for the maximum variability. In this case, we're looking for the max, the
Most
mode which
spread.
explains the maximum error.
it's the same thing. The mode that I explained to my maximum error.
So there are many ways to do it. There's just one way to do it. None of them are perfect. There's the SVD method. There is
SPD is more theoretically correct, I think.
yeah, but then there's ensemble
expensive.
common filter, which gives you.
Yeah.
Well, you could say that the TIGI probably uses the 4D1, which is SVD, right?
Most
So-
probably.
So the surface forcing is generated by 4D1 or SVD. So maybe that's giving you a better spread than reading.
That's possible, but then physically speaking, forget that part. The surface is influenced more by the forcing. That could be the physical argument rather than saying that the forcing might have captured the growing mode more correctly. That's what you're saying. So this is the mean, and the dotted lines are showing you the spreads. As I said, the spreads are very important in the expected error. So as you can see, the spreads are far lower. I would have liked the spreads to be compared to the RMSC, but they're far lower. The reason is that we have now not accounted for 2 other very important sources of uncertainty: model error and the lateral boundary conditions.
So
and apart from this, the way we have done all this could also be not very correct, and also the ensemble size. So all this thing goes into the spread.
So spread is the difference between
It's the standard deviation of the ensemble.
from the mean.
From the mean. Very, very
And
simple.
RMS error is you're comparing to high count.
Observations, correct. And you want this to be comparable. The dotted line should be comparable to the corresponding solid lines, because that is telling you that the ensemble forecast did not lie about how much error we will get. Here it is underestimating, which is very, very common in the ensemble, and one of the main reasons is the limited ensemble size. So as you can see, the underestimation is by about a factor of 2. So of course the red one has the highest spread because it has got combination of both spread due to ICs and spread due to the forcing. So the
So
spread is
I'm testing that you have a crossover at 3 days where the spread from the forcing beats the spread from initial condition.
That's true.
Beyond 3 days.
Yes. But I don't know what physical significance it has.
It is just saying that surface is much more efficient at changing ocean circulation than initial condition.
Forcing is efficient.
Yeah.
But I think as we go deeper, it will change because the forcing.
Right, because you're looking at the surface. As you go deeper, this crossover point will be much further down.
Right. So the spread is under dispersive. So this word is used in the ensemble, people doing ensemble. So it's a bit confusing for people doing ocean and atmosphere dynamics. But all it means is that the spread is less than the RMSC. So ideally, spread and RMSE should be comparable. So ideally means all sources accounted for correctly and large ensemble size. And obviously here we are not ideal. And the next one, I'm showing you the surface and also the 3D verification. So this other lines, gray and yellow and magenta, they are the same thing as surface, but they are for the verification of the whole domain. So in general, the error average of the whole domain is lower than that at the surface. And then the ensemble improves even in the verification of the whole 3D domain. But the advantages that you get are pretty small compared to the surface. Basically because over the whole 3D domain, the forcing becomes less important. And also the lower part of the ocean is very stable.
Strongly constrained.
In some sense, if you want to use that word. So there's improvement even in 3D verification. And here are the spreads. Again, you talked about the crossover point, right?
So about
Yeah, crossover point goes to the 11, 12 days.
Yeah.
That's true. Correct. So now I'll just show you the same information, but in terms of percentage improvement. So this is basically black minus the colored curve divided by black multiplied by 100. So I want to find out the advantage one gets by using the ensemble, right? So at any point, at any time point, subtract the black and blue, divide by black and multiply by 100. It will give you the percentage improvement over the black curve, which is a control. So here is the improvement in the surface, velocity field, average over the big box. So you get very little, like 1 or 2% improvement by using the perturbed ICs. But if you use both ICs and FCs perturbed, then you get this red curve, which is 5 to 10% improvement, and it's mostly due to perturbations in the forcing. So the green curve and red curve are very, very close. The magenta and yellow are for the whole 3D domain. So we get an improvement of about 7% max. So the improvement is mostly in the surface because of the forcing. And the initial condition, the improvement is similar. Now I'm showing you the improvements in the coastal region. So if you remember, I had put those green boxes, US coast, Florida, Max coast, and the central coast. So in general, the errors are smaller than compared to the whole domain, the big box. And the percentage improvement is pretty high. You get 10 to 20% of improvement in the coastal areas. So this red curve goes from 10 to 15% for the surface, and the magenta curve is showing you the 3D domain. So, but the 3D domain in the coastal regions, because shallow waters is, almost like at the surface in some sense. Now I am showing you the improvement in the loop current region. Okay, and obviously, you see that the errors themselves are pretty high, okay, compared to the coastal regions. There is improvement, but the percent improvement is pretty small. It's about 5 to 6%. And if you look at the initial, so for the coastal regions, the improvement due to the ICs was very small compared to due to the FCs. So the green curve was very high compared to the blue curve. But in the case of the loop current region, you get comparable improvement. The green and blue are more comparable. So in the loop current region, the ICs improve the RMSE a bit, because there it is chaotic, very nonlinear, and the ICs become very important compared to the coastal areas. So now I'm showing you the RMSE, spatial structure of the RMSE. So that was, earlier I showed the graphs were like average of the whole domain. So here I'm showing you the RMSE in the control. So at each grid point, I have averaged over the 15 days of forecast and then averaged over the date time groups. So most of the RMSE is in the loop current region, as you can see. And the coastal regions have very, very comparatively low errors. So I'll show you the spatial pattern of percentage improvement. So I showed you the percentage improvement averaged over the whole surface. So I'll show you the pattern, which means first do the improvement for each grid point at the surface, okay, averaged over the 15 days, and then average over all the dead time groups. So the top left is showing you the improvement or not, or the degradation using the first ensemble, the ensemble with only ICs perturbed. So it's the percentage improvement over the control with respect to the mean of this ensemble. Okay, so you see that if you perturb the initial conditions, the main advantage that you get given by the green color, it is in percentage, is close to the loop area, is in the loop region, and also this kind of eddy structure to the left of the loop region. I have not shown you the bread vector mode from these experiments, but it looks like this basically. You get the loop current, which is very obvious, that's what you should get, but you also get this eddy-like structure on the left side. And this is the regions where you are getting most improvement using the perturbed ICs. Then top right, you see the percentage improvement you get by using the perturbed forcing. And it's mostly in the coastal regions, and in the loop region, it doesn't improve at all, actually.
They look very complementary.
Complementary, yeah. And when you combine the two, you get this picture. You get an average of about 5% of improvement, which we saw in those curves also. And I've put here the 100-meter bathymetry curve. The point is that this perturbed forcing does very well along the coast, very, very close to the coast. And in general, the improvement is most along the coast, as can be seen, but it's also kind of in between these two eddies, the loop current eddy and the left eddy that I talked about, which shows up in the bread mode. So that's the spatial distribution. So reduction in errors is mostly due to perturbed forcing, and highest reduction in shallow coastal waters, Florida, South US, and North Mexico.
Well, basically where the eddy is not active, I guess.
You can put it that way. It is shallow, and also the velocity magnitudes are smaller, all these things. So now comparing the RMSE and the reduction percentage, the improvement percentage. So highest reduction in shallow coastal waters, these areas have low RMSE. So wherever you have this dark green color in the improvement, you have very, very light pink color in the RMSE. So what this is suggesting is that model error and LBC's error is not important in these areas, right? Because we are only accounting for forcing perturbation, forcing uncertainty, and we are getting a very good reduction. That means most probably in these areas, the model error, and I mean, this is not a very strong conclusion, but it suggests that the model error and lateral boundary conditions are not important. So now I'll talk about the Lagrangian sensitivity experiment or verification experiment. So this is a separate experiment. The domain is slightly different, and the product used is quite different. So this experiment I'm calling 3 to 9 kilometers. It uses the HiCom high resolution 3 kilometer analysis product. So the ROM grid is 9 kilometer resolution, and the domain is slightly smaller. This product is available every hour, and floats are released at every 9 kilometers on 20th of April on each of the dead time groups. Sorry, not 20th of April. Each of it. And offline tracking algorithm TrackPy is used to generate observed tracks using the high-res hourly product. So the reason for changing over to the high-res product is that the 9 kilometer product that I used in the whatever I talked about just now is available only once a day, 24 hours. And to do the Lagrangian experiment, I need observations of the tracks. So if you release a float, where it will go in the observations. So 24 hours is very coarse for the offline algorithm. You'll get a lot of errors due to coarse resolution of the UV field in time. So I have to switch over to this 3 kilometers resolution product, HiCom product, that is available only for the Gulf of Mexico. It is not global. Okay, so Jason designed a new grid for this, and I did this experiment again not all the datetime groups, but only one datetime group. So the RAM grid is still 9-kilometer resolution. So I had to emphasize that 3 kilometers has been interpolated to 9 kilometers to generate ICs and boundary conditions. Okay, so this is not a 3-kilometer resolution experiment. It is 3 to 9. We're going to find from a finer to a lower resolution. So what I will talk about, the experiment is only for one datetime group, which is not averaged over many datetime groups. Other datetime groups are running, so we will see what we get. So floats are advocated for 15 days using the control, ensemble, ICs and FCs. So again, the same set of experiment has been done, but in this experiment we have released floats at every 9 kilometers in the domain. So to emphasize, 3 to 9 kilometer experiment has the same resolution as 9 to 9 kilometer experiment, but has a slightly smaller domain. It is smaller by about 4 degrees in latitude. So here are the errors comparing, RMSE errors comparing the 3 experiments. So look at the solid lines first. So I'm comparing the RMSE for 2010, April 20th, for these 3 different cases. So 2 different cases. And I have done one more experiment for this particular datetime group, that is 3 to 3 kilometers, also a high resolution run. So ROM's resolution itself is 3 kilometers in the third case. And each experiment uses a different analysis product for verification. So you have this green solid curve, which corresponds to the experiment that I discussed just now, okay? Because this goes from 9 to 9. The global HICOM is used for this. And the cyan and the blue correspond to the 3 to 9 and 3 to 3. See that the point is that the cyan and blue curve are very close to each other. And in general, the cyan and blue both are above green. So using the 3 kilometer products is giving me higher RMSE.
What's your verification? It's still 9 kilometers.
Yeah, the verification is different for each analysis. For different experiment, so whatever product I used to generate the ICs for this 9 kilometer, I'm using for verification for the green curve. I use the 3 kilometers product for the cyan and the blue, interpolated to the 9 kilometer grid in case of 3 to 9 and interpolated to 3 kilometer grid in case of 3 to 3.
Okay, so the verification is on the same grid, but it uses a different product that's consistent with the initial condition.
Yeah, so the verification product is consistent with the product that created the initial conditions.
So this, this to be sensitive, you say interpolated.
Well, generated by the code that generates the.
Yeah, but you have aliasing, right? If you got a 3 kilometer feature and you're putting it in the 9 kilometer grid by subsampling in some sense, and the 9 kilometer model is not going to evolve that fine feature accurately. So you don't verify against it later. Because you know what's aliasing?
Yeah, but the thing is that even in the verification product, the 3 kilometer has been interpolated with 9 kilometer using the same code or whatever.
Right, but the aliasing is kind of random, so it introduces a random error. Let's say you have a small feature, okay, that's not resolved in the 9 kilometer grid. You interpolate it to the 9 kilometer grid. It appears somewhere, but the 9 kilometer model does something random with it. The 3 kilometer model moved the feature somewhere else, and the 9 kilometer model doesn't get it.
Yeah, but then why does the 3 to 3 have the compiler error with the 3 to 9? 3 to 3 should not have that problem, right? That's why I did the 3 to 2. Last time you said this. So that's why I went ahead and Jason designed a new script, and then we did the 3 to 3.
So which are the 3 to 3?
Cyan and blue. So cyan is 3 to 3, blue is 3 to 9, and green is 9 to 9.
Okay, so that augmented. Maybe the overall error then is higher for.
It's possible.
Again, it's smaller features, so
right.
The error growth may be higher.
Right. At this experiment, because I want for this Lagrangian experiment, I wanted to use the hourly product to generate the tracks. So I had to choose between 3 to 3 and 3 to 9, and because 3 to 9 is lower cost experiment, I just went with I'll show you 3 to 9.
The thing is, there's no unique way to interpolate from 3 to 9 kilometers, so it's not clear what's the best way. Right.
Each one will give a different answer.
So if you have a fine feature, if you just take them and put them on the 9 kilometer grid, probably don't. But if you average, then you smooth. So each one has some bad features.
Right. The need to do this experiment is simply because the analysis product is not hourly in the case of experiment that I showed you, and I want to generate observed tracks. So, and the dashed line in this is the corresponding ensemble experiment. The dashed green is the ensemble experiment with 9 to 9, the one with the perturbed forcing. So it improved over the control as I showed you. Now the ensemble mean is also improving in the case of 3 to 9 and 3 to 3. But overall error is higher and the improvements are a bit smaller. Okay, I just wanted to show you this curve so we get an idea of. So now I just did not look at 3 to, I just stopped in 3 to 3 because it is not giving us any advantage in terms of. So for this Lagrangian I'm doing 3 to 9. In 3 to 9, let's look at the
3 to
improvement.
9 is also worse, right? It's not any better.
Than the green curve.
Right.
Yeah, but the point is that both are worst, 3 to 3 and 3 to 9.
Right.
Then why not go with 3 to 9 because it saves a lot of computational time.
But you never use 3 to 9 in practice because it's not better than 9 to 9.
In practice, no, but here the application is to do the Lagrangian tracking. So the point is that this product 3 is available every hour. That's the main reason. So the improvement that we see, blue solid and blue dashed, I'm showing you the spatial pattern of that. Okay, so if you perturb only the initial condition, this is what we get. So this is similar to the 9 to 9 case, in the sense that there are two big eddies showing you improvement. And in the earlier picture, if you remember, for 9 to 9, there was no brown color here at all. So we are getting some degradation also by using perturbed ICs. And if you use perturbation in both IC and FC, you get this picture, which are about 6% of improvement. And again, compared to the 9 to 9 case for this particular daytime group, it is not that bad. You do get some brown color, which is absent in the 9 to 9 color, but overall you get an improvement. And again, you get improvement near the course. Okay. Now, the point is that I have put floats at every 9 kilometers. So the floats have been advected by the control and by the 3 different ensemble experiments. So I got 3 different ensemble means. So 3 different mean tracks, 1 control, and I got the observation generated with the offline algorithm. So let's look at one of these in a particular location over 15 days. So in this case, the yellow is showing you the observation, the track stats over here. Okay, the black is showing you the control. The blue is showing you the mean with the perturbed ICs, green the mean with the perturbed FCs, and red with the perturbed ICs and FCs. And the other 2 pictures are showing you the ensemble corresponding to the perturbed ICs and FCs, that's the red, and perturbed ICs is the blue. And the point is that the black curve does horribly. The control float goes very, very far away. Okay, the point is that if the Eulerian velocities have improved, there should be some improvement in the Lagrangian tracks. And I'm just kind of cherry picking one example. The perturbed ICs improved slightly, but the perturbed forcing improves a lot. This is near the coast, by the way, the Mexican coast over here. And if you combine ICs and FCs, also it is very close to the observation. And this is the 15 days.
So you're advecting the trajectory to flow to the ensemble mean velocity?
Okay, so the ROMS forecast, what I have shown was Eulerian, everything.
Right.
So this experiment, what I do is I release float at the beginning of the week every 9 kilometers, and these floats are advected inside ROMS, inline.
Okay.
And this yellow guy, this is the what I'm calling observation is actually generated offline using the HiCom 3 kilometer hourly product, which I'm using for verification, Eulerian verification. Okay. And because this is hourly, the TrackPy algorithm, I know that it does pretty well. And so this is all about Lagrangian. Whatever verification we did in Eulerian, we just want to do it for Lagrangian. That's the motivation.
So, but blue one.
Yeah.
How do you get the blue one?
So this is the perturbed ICs, the mean of that.
The mean trajectory or the
The mean trajectory of the ensemble trajectories generated using perturbed ICs in ROMS.
How do you average trajectories? I know how you average velocity.
Yeah, I average the lats and longs.
Okay, that's weird.
But it can give a weird reasons.
Yeah, so I'm curious. How do you average a trajectory?
Yeah. So the mean can lie outside the
No,
ensemble.
but suppose I have a float which goes this way and a float that goes this way. The average is in the center?
Yeah. By the way, the way I am doing it.
Again, that seems probably more than one way to do that.
There might be one more way to do it because of other ways to do it. Because many times what happens is that if I find out the mean of this, see this red mean is lying outside the envelope in some sense. So
You're looking at the center of mass, basically. Like,
Yeah, something like that.
yeah, but the point over here is, does the Eulerian improvement reflect in the Lagrangian? And so I'll show you what I have done.
You could also do one thing to take the ensemble mean velocity and interact with that velocity. That's a different way.
Yes, using the offline.
Yeah.
To see if one gets different, or how different rather. Yes, that's possible. That's a good.
I'm not sure
that's
that's
a-
better, but that's just
no, that's a good idea actually, because what is happening is this TrackPy, even with 1 hour velocity frequency, has its own error, just because it is coarse in time. It's not 1 second. Now, if I do what you were saying, that would be kind of good, because then I'll provide hourly UV values from ROMs to the TrackPy.
I think it's more physical. It's more physical because you're not averaging over trajectories now.
Right.
No, I'm not sure. I'm not saying it's better actually. I'm just saying it's a different way.
It's
to do it.
it's different.
I think it depends what you
Yeah,
what
depending
you
on what
want to
you
look at, because the center of mass gives you an idea, but the general, movement is there is a trend. If basically all the flows.
Yeah, actually, you could think of that as not the average of trajectory, the center of mass.
Yeah.
as you say.
But then the first momentum gives you an idea of the spread.
Right.
So it would be nice to see both to some extent.
Yeah, I'm not showing the spread here general, but it is very, very small. I'll show you in
Okay,
average.
that would be good to look at. Then, so.
Yeah, but the thing is that if you do the ensemble average velocity, then you can't do that inside the ROM anymore. You have to do that offline.
Yeah, that's what I said. If you want to do the ensemble, use the ensemble mean ensemble velocity, then it has to be given to the TrackPy.
Right, you're definitely going to, yeah. I think you're going to reduce the spread quite a bit, probably.
Spread of what? Once you have the mean, there's no question.
Yeah, because you eliminate a lot of uncertainty in the velocity field, right?
Right. So the way I'm quantifying this is, so we want to see the endpoint after 15 days where it lies. Okay. So we want the endpoint of the forecast to lie very close to this LO dot for this particular point. So I simply calculate the distance from this black endpoint of the black trajectory from the endpoint of the LO. That comes to 217 kilometers. Okay. And for this blue, red, and I do the same, and I find out how much it improved upon this distance. So this is 117. Distributed in the blue and the LO is lower than that. So whatever that is separate from 217, the improvement is 45. The improvement for the red guy is 183. Okay, so the distance. So I'm giving these figures in terms of improvement, subtraction. If it degrades, then you get a negative value.
So in the real world, so people really want to do oil spill forecasts.
Yes.
How they do that? Do they run the model actually vecting the trajectory inline, or they actually take the velocity actually vecting the oil spill offline?
Yeah, the papers I saw with this NOVA operational team, Chris Barker and some other people I met, and I got hold of their papers. They are mostly doing it offline.
Okay, I mean, if it's offline, then there is some merit to actually do the things, doing things offline, because that's the practice they've been using.
No, but here the main question we are asking is whether the ensemble, is there some value in the ensemble? That's the question we are asking.
Right. Right, I understand that, but what I'm saying is that if they are doing this kind of analysis offline, then it does make sense to predicting the velocity field first, and then do the Lagrangian prediction offline, and you can do the ensemble average of velocity to do the direction versus the individual velocity.
Right. That's more of an operational question of how to save time and all that, because this question was asked to me by an operational person during the conference.
Right.
The ROMs runs and all that. But that's more of an operational detail, whether you want to do offline or But this is more like science, whether the ensemble is helpful or not. Okay. So now for the Lagrangian, I was showing the figures in meters per second and percentage improvement. Here I'll show this improvement in kilometers because that makes more sense. So remember this control minus the where it ended up between the observation, and the other tracks, other endpoints I will show as improvement on the control.
So you only one case.
One daytime groups, but these floats are everywhere in the domain.
But you probably need a lot of groups to come up with the
Yeah,
statistical.
yeah, I know.
results.
I'm running the other.
Okay.
So in this also for one daytime group, the floats are everywhere. Okay, I will show you the average.
So I understand they're everywhere, but it's just one case.
One case, one daytime group. That's right. I'm doing running. So here is the RMSC for the Lagrangian case. So the y-axis is in kilometers. This black line is the control, and if you see that the ensemble mean is improving by about hardly by 20 kilometers. That, I mean, for the Eulerian case, it looked like this, but in terms of kilometers, we have a feel for it. So 20 I mean, there's not a scientific way of doing it. I have to do the significance scores, but still it looks pretty small. And more importantly, the spreads are very, very small. Remember in the Eulerian case, the spreads were smaller by a factor of 2. Here, the spreads are smaller by many more factors. So it is not, the ensemble is not spreading out as much as we want them to. So the Lagrangian Eulerian, there is no one-to-one mapping. If this improvement Eulerian doesn't mean an improvement in Lagrangian. But if you look at the coastal region, you get quite a big advantage in about 35-40 kilometers improvement using the ensemble mean compared to the control. So again, in the Lagrangian, I mean, there should be some relation between Eulerian and Lagrangian. So because the improvement in the Eulerian field in the coastal region is very huge, you get quite a big significant improvement in terms of the Lagrangian trajectories. So this is the control distance. So we come to know where the errors are in the Lagrangian. So this is a 15-day difference between the endpoint of the observation and endpoint of the control trajectory. And you see that most of this error is again the loop current region and this big eddy over here.
How do you make this plot? You take the difference between the endpoints and put it at the starting point?
So on the 15-day, so I show you this,
I
right?
don't understand how you made the picture.
Yeah. So this is for one float, one particular location.
For one floor.
So this yellow minus black, you do it for all the locations.
But you put it at the X.
Yeah, I put it at the
Okay.
initial point. That's right.
Okay, that's
Yeah,
what I wanted.
yeah, okay. I don't understand the question. Yeah, at the initial point where it originated.
The origin.
Yeah. So the loop, wherever the floats starting off in the loop current region have a pretty high error, and also near this US coast they have a high error.
So this is like the Lyapunov index.
In the Lagrangian space.
Yeah.
No, but there's a difference. The Lyapunov thing you do using only the model. There's no observation involved.
Also, you do it in phase space, but if you're doing a physical space.
No, but that's not the point. The point is for Lyapunov, we don't use observations at all. It's model, totally the model.
Right.
You put on the initial condition and see the spread.
So if you plotted spread, that would be Lyapunov.
That would be the Lyapunov. This is not Lyapunov. This is RMSC. And the spread is very low, as I showed. If I do a spread graph like this, it should look like this. But it's not looking like this. It is smaller, like at 100 kilometers. So the spread is underdispersive, as we saw in the Eulerian. But the Eulerian underdispersive spread translated into a huge deficiency in the Lagrangian framework. That's the point.
So what are the area there's no color at all? There's some area.
Yeah, the thing is that these floats pass out of the domain.
Oh, okay.
So just to be consistent, I just put nans there. After some of them pass out on the 15 days, some on the 12 days. So that is why there is
What about the floats? What about the NAN regions in the
Right.
Gulf of Mexico?
Here, these one pass out of the domain, and this over here I have not. I knew that these guys will definitely pass out, so to save time, I did not put floats there at all.
No, are there any missing values in the center?
Yeah, here there are missing values because the float that I put here, it went out of the domain.
Okay.
Goes on the loop current, right?
Yeah, I mean in the loop current also, do you see like 15 days it cross?
Yeah, that's
Why you have these regions, right?
Oh, okay.
Wherever the floats are put in this region, which is actually the ocean, is not land. They went out of the domain, and So when I separated, I got a none, and I just had to keep it as it is,
Okay.
just to be consistent.
But isn't this is the thing that the distance is really big? You can actually color using different thing and saying this is the really large distance.
Yeah, I'm not showing you the distance traveled over here. So we can make a graph that correlates the distance with the spread also.
Right.
Yeah, so in the next graph, I'm showing you the improvement in the Lagrangian tracks using the ensemble mean. And as you can see, so the top right is using the ICs only, the mean using the ICs only. So this is the same graph that I showed you earlier map, in which in the Eulerian case I did an improvement graph, right? So red and green or something like that. So I'm doing the same thing, but in terms of kilometers. I'm not giving in terms of percentage. So if you remember in the Eulerian case, you had a lot of red color or had white. Usually you did not have negative. But with the Lagrangian tracks, I'm getting a lot of negative values. But again, the average works out to be positive in most cases. So as you can see in the coastal regions, you get red color. So we get some advantage over there. So if you look at the advantage you get in Florida and Max Coast, the center in the table, you get an advantage of 35 kilometers in both using the mean of the ensemble perturbed ICs and FCs both. Okay, so this is the advantage you're getting. But if you go to the central coast area, it's either negative or you get a small positive number. But and if you go to the loop, on average, we are improving. And if you do an average of all these values over the whole box, I get improvement about 20 kilometers. So this calls for basically significance testing. And I think that what we will end up is that along Florida coast and this Mexico coast, I'm going to get the most significant differences. And rest all might be a bit iffy.
So the improvement in the central coast is not obvious, right?
Pardon?
In the central coast, would you call it the central coast?
Yeah, it's not. It's green and red. And again, one more thing is remember that this is based on only 120 time groups. Okay, the others are running.
Yeah, but there, I mean, I think physically it makes sense because I think in the central coast that's actually under a lot of influence of the eddy too, because that's where the eddy actually winds up when they die.
Right, but we see this eddy that is a permanent structure there actually. The loop current to the left of the loop current. There's a weak eddy, big one.
Yeah, but the eddy would propagate westward.
Right.
After I mean, the west coast area is actually the region where the eddy dies.
Right.
So you have a lot of eddy influences. This is the coast you're going to see a lot of eddy influence. Where in the northern coast and the southern coast, I think you actually see much less eddy influence.
Right. But your point is that wherever there's an eddy, the perturbed forcing is not going to help you, right? That's what you
Exactly.
Yeah.
Once you have eddy things, and then the forcing is not going to be helpful very much.
Right. So as far as being helpful is concerned, the ensemble being helpful again and again in everything. The East Florida, the West Florida coast, and this Mexican coast is coming up again and again. So we have to make that point pretty strongly. But other things are a bit iffy. Yes.
Yeah. You also need to look into the surface currents in that region. See, the one problem with that Florida Strait and the other coastal region is the possibility of surface currents to go in different ways is pretty less. So that may be one of the reasons you say, like.
Oh, you mean to say they are kind of, yeah, but that's just saying that it's not eddy-like, right? In other words, it's very laminar in some sense, right? Laminar.
So in all other regions, especially like the place and even to the close to the central coast, like slightly top ocean and it's also eddy region. So you can have different possibilities.
Yeah, but I don't understand that with the US South Coast though. Why doesn't the same logic work with the US South Coast? That's also coastal, right?
US South Coast.
Yeah.
That's also green color. Active because there are a lot of eddies associated with the freshwater influx and all that.
Yeah, we have to make some rationalization about this.
So if you compare this with time average surface currents or something, you could see some signal.
So that probably has something to do with the freshwater into the Mississippi River plume.
The US South Coast, you mean?
Yeah.
Okay.
Well,
so,
some of the fact that you're getting the positive and negative, this is less robust to measure compared to your previous measure.
No, it's the same thing. That I expressed as a percentage. So if I had divided this by the control distance and multiplied by 100.
But there you didn't get positives and negatives that much. To either 0 or positive.
That's what the negative thing was there, but
To very
all was
small.
almost positive. But then again, this is a different experiment. Okay, I'll show you the Eulerian and Lagrangian. The next slide, things will become more clear. So for this particular experiment, I'm showing you the Eulerian improvement in the top and the Lagrangian improvement or degradation in the bottom.
Okay.
So this is a better, yeah.
So in this metric, you are mostly looking at the displacement with respect to the control trajectory.
You can just say, think of it as simplistically, very speaking, how far did the control trajectory end compared to the observed trajectory?
Is there any value in adding the direction also?
Yeah, definitely. Definitely. That's one more metric that would be very interesting. And I did not do it because I think in some, well,
Oh, the direction?
yeah, he has a good point. So what he's saying is that I just look at the distance, right? So he's saying look at do a theta kind of this thing. So control is going, yeah, we had talked about this with Ping. Control is going here, say, and the ensemble mean is going there, and the observation is going there, say. So what I'm doing is differencing this. What he is saying is find out this theta, find out that theta. And suppose it is going opposite, compared to the observation, you get 180 degrees.
It might show some.
Yeah, it will show. I mean, I thought about that already, but as a first look, I think this much is enough.
Yeah, I think initially people care about how much off it's by distance.
No, but it's related, right? Distance and direction are related.
Yeah.
So this makes
If
more
it went in
sense.
an opposite direction, not
Yeah,
very
this-
far away from the initial point,
Then you are okay with the distance.
No, my point is like, all these ensembles are spreading sporadically everywhere. Then this makes sense. According to line 2.
No, but you're looking at the mean, right? So you just have one line for the ensemble also. Mean, just take the mean trajectory and find out the angle. So all this is saying is that I'm interested in where it ended up. That's one thing. But I would also like to know whether actually the direction was right. If you lost something over in this region, and if the control is telling you to go north 20 kilometers, okay, and the observation is actually go down south 20 kilometers.
It's not like, yeah.
So that theta will tell you that.
Theta is a tricky thing to do because you can't go to 360, you can go to 180.
Yeah, but we can map between 0 and 180, right? What's the
Yeah, I guess-
difficulty in that? With 180, you can clearly, if you mark black areas with 180, you can clearly see where the control and observation are doing exactly opposite things. So let's move on with this. So this is a very short last section. So the actual aim of this whole work is to sensitivity of oil transport to oceanographic and forcing states for this DWX field, which I did not speak about so far. But so far we just established that there is some value to using ensemble in which you account for perturbed forcing and ICs. That's all we showed. So in this I have done 3 different experiments using HICOM analysis. So there are 3 controls simulation experiment. 2010 with ECMWF forcing, 2010 with CFSR forcing, 2013 with ECMWF forcing, 3 different years. And then there is an ensemble experiment for 2010 in which ICs from bed vectors are used and ECMWF analysis ensemble analysis are used. So on 20th of April 2010, I have got a HICOM analysis. I launched a 5 months simulation from that. It's not a forecast, it's a simulation. And also have got the perturbed ICs from bed vectors. So in the ensemble experiment, I use the ICs to generate 20 ensemble members and do a 20-member simulation. So in each experiment, what I do is the floors are advected for 150 days starting on 20th of April. So 5 months. The floors are advected till 17 September. That is about 90 days because that's when the thing was sealed in 90 days. So the floats are released only for 90 days, but they're advected up to 150 days. So floats are released at the rate of 50 per hour starting from 20 April for 90 days. These are released at random locations inside a 0.25, 0.5 degree box centered on the on the oil spill site. So float release date is 20 April, float release stops is 20 July, and I am tracking all these floats for 5 months. So 20th of April is tracked for 150 days. The floats released on 21st of April is tracked for 149 days, and so on. So the lead time gets shorter and shorter for the floats. The forcing is generated by stringing together atmospheric analysis at 0, and 12Z for 150 days. So that's why I'm calling this a simulation, not a forecast. So I take the analysis every 6 hours and make a string is the wrong word, but
Time series.
time series is the right word, time series, and use that as a forcing. And these are ensemble analysis. So at each time I got 20 different copies. So I'll show you statistics of oil escape. Yeah, can you see this line in the Florida Strait? So if a float crosses this line, I'll count that as escape to the Gulf of Mexico, because the chance of it coming back is almost zero practically. Okay, so I'm using this line as a criteria. So when I say exit the Gulf of Mexico, I mean this line. And I'll show you the amount of oil in this box as a function of time, and these two boxes also, but mainly this box and the amount escaped.
Amount of floats here.
Yeah, in terms of percentage of total floats released. So I will quickly show you the animation. Yeah. So the top two panels are for 2010 with different forcing, and this is the control run. All these are control. The bottom left is for 2030, the same date.
So you're putting a black dot for each float. Is that
That's right.
Okay. So but typical is that you don't get the concentration of floats. You just have destiny.
Hmm?
If they're at some point the concentration saturates, right? Concentration of floats.
You mean to say in the picture?
Mm-hmm.
I did not do a density thing at the
Okay,
contouring.
that's what I was getting at. Okay.
Yeah, I tried that, but it is not giving us any more information, or
Okay.
making the picture pretty. So I dropped that and I'm just plotting the floats as that. So the interesting thing over here is, for the 2013 case, the oil makes the Florida Strait faster compared to the 2010 case. But less oil escapes through the Florida. I mean, there are different states of the ocean. So there is no point. I mean, we are trying to capture the general thing using 20 ensemble members or 3 different years, because there are so many different states that are possible. We can just talk about what we observe. So there's nothing general about this. But the point I'm trying to make with this one is, compare top left with bottom left, 2010 and 2013. Though the oil makes it faster at Florida State, far less oil escapes because the loop current happens to separate very, very close to the strait. So the oil gets diverted basically towards the left. And if you're concerned about oil escaping the Gulf of Mexico, so that's a saver. And one important thing, which is obvious, but we should make it the point, that it's just the geostrophy that is preventing the oil from entering this red area. Because if it enters the red area, it goes out of Gulf of Mexico very, very fast. But that never happens, simply because the vortex is very tight. And see, the DWH site is very, very close to the northern end of the loop current. And no oil goes into the red, which is, so we are kind of skating on thin ice over here. So the leading edge of this red thing is very, very close to the oil spill, but it never quite makes it. It goes around it, and because of the separation, the oil goes towards the left in both the cases. In 2013, it's quite kind of dramatic, because the oil makes it here, and then the current separation happens exactly over here, and a lot of oil gets diverted, and hardly anything goes to the Gulf of Mexico, out of the Gulf of Mexico. So I'll show you one or two graphs now about this.
It looks like escaping Gulf of Mexico is maybe a good thing, because getting away from the coast.
Well, that's a different debatable point. I mean, it depends on whom you talk to. So
If you look at it, it's just
it would have gone to the coast. So
otherwise, it's getting bunched up at the Florida coast in
That's right.
2013.
Yeah, you won't end up in other coasts because Gulf Stream is super fast. So
Yeah,
it will be taken away to the interior of the ocean, open ocean.
right. That's what we want.
right, and kind of get diluted, right?
Yeah, if you get it away from the coast,
Yeah, I mean, it's just a question of who makes the hype about this. When it happened, a lot of articles on escaping Gulf Stream and reaching Greenland and so on and so forth.
yeah, we will be diluted by the time it gets there.
Yeah, so that's what it's from. It was not as big as a deal as people made it. Anyway, so this is a statistics about how much of the oil escaped the Gulf Stream. So on the Y-axis I have got percentage of oil released, amount of oil escaped as a percentage of total amount of oil released. Okay, so if there are 100 barrels of oil total released, this is 5 barrels, 10, 15 barrels, and so on. So it takes quite an amount of time, about August 11, to make it close to the Florida Strait in the first place. So the blue solid, black solid, and red solid are for the 3 control runs. The 2013 is the red. The black and blue both are 2010, one with ECMWF forcing, other with CFSR forcing. And as we saw just on the animation, the red curve, a lot of oil starts escaping the Gulf of Mexico, but then the separation happens around August of 11th in 2013 case, very close to the strait, and the oil gets diverted. But in the 2010 case, after 15th, after August of 11th, a lot of oil gets into the Gulf Stream, and the cyan are the 20 different ensemble members, having 20 different perturbed forcing and 20 different initial conditions. And as you can see, there's a lot of variability in this. So it can be anything between 7% to 20%. So right now I'm trying to look at, try to explain why ensemble member 14, more oil passed, and why ensemble number 6 less oil passed. But it's kind of complicated. You have to look at velocity fields and all that. So here, box 3 is the box near the US coast. So oil at any given time in that box, obviously it goes on increasing and drops when it is sealed, and the oil moves away from the US coast towards the strait, Florida Strait. So you get a peak somewhere in between.
What's the other box?
So these are near the western Florida. 2 small boxes near the western Florida.
So the huge spread there, just like in the case of.
Yeah, that is because this is very close to Florida Strait, this box.
Okay.
This box is actually, I wanted to see a kind of piling up effect. So just close to the Florida Strait north, I put a small box. This is the southwestern tip of Florida. And you see a similar thing as escaping. So just 2 points. Geostrophy is preventing the oil from entering the high-speed loop current.
Why would you say geostrophy? I would say the vorticity.
But it's kind of, the flow goes around the vortex, right?
Right, vortex isolation, that's probably the term.
Okay.
Geostrophy defines all large-scale flow, right?
Okay.
And all large-scale flow in the ocean is geostrophic. So is vortex isolation, vorticity isolation is
The better phrase.
maybe, yeah.
Yeah, I think we should say this, though this might be very obvious, but nobody has said this. I mean, the DWS site is so close to the loop, and still the oil doesn't go, which is kind of remarkable. In 2013, the separation of loop current close to Florida Strait prevents oil from entering the Gulf Stream. We saw that. To analyze extreme ensemble members in detail, why we get such different, and find a case a year in which the loop current remains intact, does not separate. This is giving me a lot of headache. I ran like 3 or 4 different years. I don't know a priori because maybe it's not separating in the HICOM analysis, but once I run ROMs, it separates out. So there is no a priori way of doing this, finding out whether loop current separates or not. So I'm going to try a different season. Does anybody know if there's a part of the year in which it is less likely to separate?
You can look
Ping,
at
do you know?
there's a database of loop current eddies. There's a
Yeah, I looked at
site which lists all the loop current eddies. You could pick those dates when there is the opposite of that. Right. That's one way to guess.
Yeah.
I think you just have to keep trying until you.
Yeah, but because that would be a very good comparison. That was the first thing that came out, that I should do that experiment, but I'm not finding the right here. So the conclusions are 5 to 10 improvement in RMSC in the surface velocity field in Gulf of Mexico, 10 to 20% improvement in the surface velocity field in coastal areas. The improvement is mainly due to perturbed forcing. The improvement in Lagrangian tracks in coastal areas is about 35 kilometers. In the worst case scenario, no evaporation, the amount of oil escaping the Gulf of Mexico through Gulf Stream varies from 5 to 20%. And the location of loop current separation plays an important role in deciding the escape volume. Thanks. Any questions?
Ping, do you have questions?
No, I think I've seen a lot of those already. I
Yeah.
think,
Any more questions?
Hmm.
Pretty late. Okay.
Okay, thanks.
Do we have a seminar next week?
so, Vikram, when are you leaving actually?
Yeah, so my ticket is on 21st of May.
21st?
Yeah, but I might leave College Station before that, a couple of days before that.
Okay.
I'm going to talk to Istvan and let's have a meeting with you and Istvan. I think you are on that Monday, right, in College Station?
I'll be back Monday. Actually, there's a meeting in Austin. I have to probably go. So I may be able to come in the morning though, Monday morning.
So which days are possible, Monday and Tuesday for you?
Tuesday it will be a lot better.
Okay, I'll talk to Istvan and let's fix that up.
Okay, Tuesday would be a 19th, right? Yeah.
Yeah, and the only major thing remaining is this Lagrangian thing and looking at the dynamics of error growth. And
Yeah.
Jingzhou is leaving for China in a week, so next week I have to sit with him and do the dynamics part.
Okay.
So that's just one section. Other, I think more or less I know what to write.
Okay.
Thanks.
Perfect.
I'll give it after placing.
We unplug the USB.